this conjecture says that for every pair of real numbers, alpha, beta, the infimum over the natural q's of q times double bar q alpha. Double bar is the, do you see here? Yeah. Is the distance to the nearest integer times double bar q beta is 0. So in this conjecture, I am approximating simultaneously alpha and beta by rationals. And the conjecture is obviously true if alpha or beta are rational. Or well approximable. And I remember you that alpha is well approximable when the infimum of q times q alpha double bar is 0. Which is the same, which is equivalent to say that alpha has unbounded partial quotient. In analogy to this conjecture, the Mathon-Tellier proposed the p-adic Littlewood conjecture in 2004, where they replaced this quantity double bar q beta by the p-adic norm of q. So the p-adic Littlewood conjecture says that for all real alpha, the infimum over the naturals q of q times q alpha double bar times the p-adic norm of q. This is, as usual, is 1 over the biggest power of p dividing q is 0. And as before, this conjecture is obviously true if alpha is rational or well approximable, and
2004 refers to when it was formulated?
sorry, 2004, yes. It was formulated, yeah. And for an arbitrary alpha, it is easy to show that the conjecture is true if and only if the set of numbers p and alpha, where p and alpha are fixed, and I'm moving n, has unbounded partial quotients. So I mean that there is no uniform bound for all the partial quotients of p and alpha, of all the numbers p and alpha. Some explicit and non-trivial examples have been given for each conjecture, and some progress has been done, but I'm not going to mention all the work done. I would like to remind a metric result for each conjecture and a family of algebraic numbers which satisfy each conjecture. For Littlewood conjecture, Einstein-Schindler Katov and Lindenstrauss.
You say it's true if and only if p to the n alpha has unbounded partial quotient. Is that for all n or?
For all n, yes. Yes, if and only if there is no uniform bound for the partial quotients of all the numbers Pn alpha.
Okay.
For all n, Pn
uniform,
alpha.
okay.
Yes. So Einstein-Schindler, Katov and Lindenstrauss in 2006 proved that the set of counterexamples alpha beta to Littlewood conjecture has house of dimension 0. And 1 year later, again Einstein-Schindler and Kleinbock proved the analog result for p-adic Littlewood conjecture. So they proved that the set of counterexamples alpha to p-adic Littlewood conjecture has Hausdorff dimension 0. These are results about Hausdorff dimension, and they are pretty recent. But in fact, the first significant contribution to Littlewood conjecture goes back to Cassels and Sinerton-Dyer in 1955, when they proved that the conjecture is true if alpha and beta belong both to the same cubic field. And in 1961, Peck proved the strongest statement, which says that if one alpha and beta are a basis of a cubic field, then the limit of q times q alpha double bar times q beta, sorry, I forgot main thing, q log q q alpha double bar q beta double bar is finite. And in analogy to this result, for p-adic Littlewood conjecture, Demathan and Tellier proved in the same paper where they proposed the conjecture that it is satisfied for all quadratic alpha. And in fact, they proved also a stronger statement. They proved that the limit of q log q q alpha double bar p-adic norm of q is finite for all quadratic alpha. The quadratics are a natural example of badly approximable numbers, since they are periodic and so their partial quotients are bounded. But for the cubic numbers, we don't know if they are badly or well approximable numbers. Right. So now let's focus on this result, stronger than p-adic Littlewood conjecture for quadratics, and let's be more precise on the Mathon-Antolier's result. From now on, I fix alpha, an irrational quadratic, and p a prime number. The Mathon-Antolier proved, in fact, result more precise than what I stated here. They proved that there exist infinitely many Qs, such that two things. One is Q alpha double bar is smaller than 1 over Q up to some constant depending on alpha, and the p-adic norm of Q is smaller than 1 over log Q up to some constant depending on P. From now on, every time I use this symbol, I mean up to some constant which depends at most on alpha and P. Okay. So this is the theorem, and if we denote by S the set of Qs which satisfy the first condition, then the Mathon-Antolier's theorem implies that the limit here is finite even if we restrict the Qs to the Qs in S. So the limit over the Qs in S of Q log Q alpha double bar p-adic norm of Q is finite. And 1 year later, the Mathon asked whether this limit is 0. And he gave a partial answer to his question. He proved that there exists a lambda which depends on alpha, such that the limit over the Qs in S of Q log Q power lambda Q alpha double bar p-adic norm of Q is positive. The expected value for lambda is 1, but he could not prove it, and as long as I know, there has not been any progress in this direction until now. And what I'm going to do is I'm going to reprove this the Mathon-Antolier's statement by using other methods. In both theorems, they use p-adic analysis, and their key tool is the p-adic logarithm. And I will use a recent paper of Aka and Shapira about the evolution of continued fractions in a fixed quadratic field. And this will give me, in fact, a more precise result than the Mathon-Antolier, because I will find a subsequence of Q, so a subset of S, where the limit is already finite. And I will give also a result in the direction of the second theorem of the Mathon, this time with the expected value for lambda and equals 1. Yeah. This is a joint work with Evgeny Zorin. So, right, if we want to prove the Mathon-Tellier statement,
Joint work with who?
Evgeny Zorin.
Right.
Yes, sure. I think. Yeah. Okay. So, if we want to prove the Mathon-Tellier statement, we have to show that there exists a positive constant C such that Q log Q Q alpha double bar p-adic norm of Q is smaller than C for infinitely many Qs. But this is equivalent to say, just by writing Q as Pn times R, where P does not divide R, this is equivalent to say that there exists a positive constant C such that log R plus n log P times R times R Pn alpha double bar is smaller than C for infinitely many pairs and R.
Does lambda also depend on P or
Who? Which? Who?
is this?
Here. Does lambda also depend on P? No. No, lambda depends on S. In fact, no, it does not depend on P.
And the quantifier on alpha is any quadratic irrational?
Alpha is any quadratic irrational, yes. Okay, and now in this inequality, if R is not the denominator of some convergent of Pn alpha, then this quantity here is bigger than 1/2 by theory of continuous fractions. So this inequality will not be satisfied. So we only might prove this inequality when R is the denominator of some convergent of Pn alpha. So now let me look at Pn alpha. Remember that quadratic number x is purely periodic. This means that all the partial quotient repeat if and only if x is bigger than 1 and its Galois conjugate is between -1 and 0. Now, when I multiply alpha by p squared, p cubed, I'm increasing the distance between p and alpha and its Galois conjugate. So, at some point, they will be far enough so that I can translate and such that the translated of Pn alpha bar is between 0 and -1, and the translated of Pn alpha is bigger than 1. So this means that there exists n0 positive such that for all n bigger than n0, Pn alpha is purely periodic except up to translation, right? So in its continued fraction expansion has a first term and then the period. And I'm denoting by ln the length of the period of Pn alpha, and by I will denote also by Rk, the denominator of the k convergence of P and alpha. So now if I go back here to my inequality, as I said, I have to choose R to be some RK, to be the denominator of some convergence of P and alpha. So we choose R to be some RK. Then we have that the quantity RK double bar RK P and alpha is bounded above and below by 1 over the K plus 1 partial quotient of P and alpha.
Sorry, can you explain the statement why it's purely periodic if there is a relation between x and the Galois?
If I
Can you explain why it's bounded?
No, it's not. It's classic.
maybe later I can.
Okay, you can.
Yeah. Oh. Well. Okay, so now what we want is to show that log Rk plus n log p is bounded above by the k plus 1 partial quotient for infinitely many pairs nk. And since P and alpha is purely periodic up to translation, the partial quotient repeats, whereas Rk increases as long as k goes to infinity. So we might only prove this inequality for the first period of P and alpha. So for k between 1 and the length of the period. The length minus 1 because I have the k plus 1 partial quotient. Right. And in fact, I will choose for k the last possible value. So the length minus 1. And one may think this is not a good choice because this is the choice for k for which Rk has the biggest possible value among all the choices for k. But it is also the choice for k for which the partial quotient has the biggest possible value. And in fact, it is very difficult to compute the partial quotients of P and alpha. And the only one we are able to compute is the last partial quotient of the period. And this is given by the following lemma. On the one hand, all the partial quotients are bounded by Pn. And on the other hand, the last partial quotient is also bounded below by Pn. one, the first statement is deduced from this statement here. So we have the inequality, the following inequality. And now if I just multiply by p both sides, since alpha is badly approximable, this quantity here is bigger than some constant which only depends on alpha. Right, and the first statement is proved. Now the second statement, one can show the second statement from this picture here. So as I said, P and alpha is purely periodic up to translation. So after a convenient translation, I have a purely periodic number here, which I denote by beta. And in fact, beta is P and alpha minus the floor of the conjugate.
Are you assuming alpha is purely periodic?
No, I'm not assuming alpha is purely periodic. But
Then why?
Yeah. So
why is P and alpha of this form? The non-periodic part has length 1.
yes, because when I multiply alpha by p, p squared, p cubed, etc., I'm increasing the distance between p and alpha and its Galois conjugate, right? So at some point, the distance will be far enough so that I can just translate such that the Galois conjugate is between 0 and minus 1, and p and alpha will be bigger than 1. But this means that this new translated is purely periodic. So p and alpha is purely periodic except for the first term, which corresponds to the translation. So sorry, maybe yes. This the lemma I stated here. I'm assuming this is for all n bigger than n0. Okay. So when p and alpha is purely periodic up to translation. Okay. Where am I? Yes. So this beta, this convenient translation is just this one. Translated. I have to translate by the minus the floor of the Galois conjugate. And as I said, this is purely periodic. I denote by with this, it's continuous fraction expansion. The first partial quotient is bigger than Pn because this floor here is negative. Well, and right, so in fact it is bigger than P and alpha. Okay, so now P and alpha has this continued fraction expansion plus the floor. And the last term of the period is B0, which is bigger than Pn. And this is statement 2. The last partial quotient of the period is bigger than Pn. Okay, so this lemma gives an estimate for the last partial quotient. It says that it's like Pn up to some constant. So now I have to bound this term here by Pn. And from the well-known induction for the denominators of the convergence, I can write it down maybe. one can deduce that our denominator, our ln minus 1, is smaller than the product of all the partial quotients appearing in the induction plus 1. So the logarithm is smaller than the sum of the logarithm of the partial quotient. And now, if I'm able to prove that this sum is smaller than the length of the period of Pn alpha, then I can Shapira have a result which says that this length is bounded above and below by Pn. And by the lemma, this is bounded above and below by the last partial quotient. And then I'm done. Okay? So up to this inequality, we have proved the following theorem. The limit over the q's in a subset S prime of S of q log q alpha double bar p-adic norm of q is finite. And this subset S prime is the set of natural q's such that there exists n positive such that q is of the form Pn times the denominator of the ln minus 1 convergent of Pn alpha. And in fact, this limit is not only finite, but it is also positive. So it is equal to some constant c, some positive constant c. Now, before I show this inequality in blue, let me explain why this limit is also positive. Okay. Now, if we want to show that the limit is positive, we have to show the opposite of this inequality here for all q's. But this is equivalent to show the opposite of this inequality here for all pairs and R. And as I said, if R is not the denominator of some convergent of Pn alpha, if R is not some Rk, then this quantity is bigger than 1/2, and the inequality is obviously satisfied. So, in fact, I have to prove this inequality for all the pairs and Rk. Okay? So we want here the opposite of this inequality for all the pairs nk, and again with k between 0 and ln minus 1. And unfortunately, at the moment, we are not able to prove this inequality for all nk, but if we restrict k to this value, which is equivalent to restrict q to S prime, then one can prove that the log of our denominator is bigger than the length okay, of the period, and then we are done. And this inequality here is proved by comparing this term with the denominator of the ln minus 1 convergent for the golden ratio. The golden ratio is the number which has all ones in its continued fraction expansion, and the denominators of its convergence have the smallest value, the smallest possible values. They are the Fibonacci numbers, so we know their growth. And comparing the ln minus 1 to this term, we can get this term. Okay, so the only thing which remains is to prove the blue inequality.
Use that P is prime?
If I use that P is prime, that's a good question. Well, yes, let me think. Well, in maybe yes, when I apply Aka and Shapira's result.
So when did you apply? Have you applied it already? Or?
Well, I have applied it once and here, when I said that ln, the length is bounded above and below by Pn. But now, to prove this blue inequality, I'm going to apply it again. So the proposition, which proves blue inequality, says that for all n bigger than n0, just to be sure that Pn alpha is almost purely periodic, the sum of the log of the partial quotients in the period of Pn alpha is bounded above and below by the length of the period. And this follows from one of the main theorems of Aka and Shapira in their paper. Let me fix n and denote by xi the image of the Gauss map, the image by the Gauss map applied I times to Pn alpha. So this is the number between 0 and 1, which has the same partial quotients as Pn alpha, but starting from the ith one. Okay. And since n is fixed, I'm going to forget this notation depending on n. So this is the length of Pn alpha. And so this AI now are the AIN. Okay, now the result of Aka and Shapira says that if we have a function f from 0, 1 to the real numbers, to the real line, which is k Lipschitz, then for all positive epsilon, the integral of f with respect to the Gauss Mean measure minus the normalized sum of the images by f of xi is smaller up to some constant depending on alpha, p, and epsilon, is smaller than the max between the norm of f and the constant k times Pn times a constant which depends on epsilon and another constant delta 0 . Yes, and we don't know the exact value of this constant delta 0.
Hold on.
Yes.
You're shifting the index, is that? Did you shift the index?
Yes, I just shift the index.
But that
yes.
plus 1 is not in the index.
Which one? Plus 1?
The log of AI plus 1.
Okay, no, here. Sorry? So I'm trying to prove this.
The blue thing, the
Yeah.
left hand side of the blue thing, right?
Yes?
That's a log of AI.
Yes, plus 1. But, okay, yeah, that's true. But, so I will have the sum of the log AI plus 1 is smaller than the sum of the log AI plus ln, if you want, minus 1. So if the constant in here is bigger than 1, sorry, no, if the constant here is bigger than 1, okay, then even if I put plus 1, I have that the sum of the log AA plus 1 is bounded above by ln up to some constant. Right? So
I see.
with, okay, so the proposition says
Sorry,
this, but
okay.
with a constant bigger than 1. Yes? And so we don't know the exact value of delta 0, but we know that it is bounded below by 25 over 64 and above by 1/2. So since since the integral part of 1 over xi is the ith partial quotient, one would like to apply this result with f of xi being the log of 1 over xi, so being the log of minus it, so being minus the log of xi. But minus log is not a Lipschitz function. So since the problem is when you go to 0 for the log function to be Lipschitz, we truncate at some point we have a lot of flexibility for this point, but let's say it's p minus n delta 0 over 12. And we define f to be minus the log of x if x is between this point and 1, and minus the log of this point otherwise. So now f is bounded by minus log, and it is p minus n delta 0 over 12 Lipschitz. So we can apply Aka and Shapira's result to this f, and I choose epsilon. Again, here I have a lot of flexibility, but I choose epsilon to be delta 0 over 24. So yeah, so now this quantity here is p minus n delta 0 over 24. And I have that the integral of f with respect to the Gauss mean measure is bounded by the integral of log, because f is bounded by minus log. And one can compute this integral. This is p squared over 12 log 2. So the sum of the images by f of xi is bounded above by, let me call this constant gamma, and this delta. So delta is very small, it goes to 0 when n goes to infinity. And now the sum of f of xi is bounded by gamma by plus delta times L, and bounded below by gamma minus delta times L. But f of xi is not exactly the log of the partial quotient, but it is very similar because 1 over xi is bigger than the ith partial quotient and smaller than the ith partial quotient plus 1. And from the second inequality, applying log to both sides, we have that log of ith partial quotient plus 1 is bigger than minus log xi, which is bigger than f of xi. So the log of the ith partial quotient is bigger than f of xi minus 1. And from the first inequality, applying again log in both sides, we have that the log of the first partial quotient, of the ith partial quotient, is smaller than minus log xi, which is f of xi if we are in this second situation. And if we are in the first situation, we have to use that all the partial quotients are bounded by Pn. This is the lemma. So again, taking log in both sides, we have the same inequality in here. And now the sum of the logs of the partial quotients are bounded by above by the sum of the f of xi, which is bounded by a constant times L, and below by the sum of the f of xi minus L, and because this is bigger than 1, it is bounded by a constant times L. And that's what I wanted to prove. Thank you.
Any questions?
Is there a geometric interpretation of Akashapira bound?
A geometric, you said?
Geometric.
This bound?
Yes.
I don't know.
So in the paper they have sequence of closed geodesics. So for each Pn alpha, right, an associated closed geodesic, and then we look on the sequence and look how they distribute it in the modular surface. And then that's somehow equivalent. I mean, this result is equivalent to.
Why is it Lipschitz? It looks like the derivative is going to infinity.
That-
Cut off, right?
In here?
So
Why
this
f
function
is
is from 0 to 1, defined on the interval from 0 to 1.
Yeah.
But as you get closer and closer to 0, oh, it's
No, no.
constant there.
It's yes. When you get
Oh, sorry.
that's the point.
Oh,
When
that's
you
a
get closer
constant.
to 0, you define it
Okay.
that the log of as the log of
Okay,
this
sorry,
one.
sorry.
It looks like excursion to the cusp somehow. Cutting off part. I guess it corresponds. Any other questions? Okay, so let's think PALOMA again. Okay, and we have, I guess, now very, very informal form by